Hello, we welcome you all to this another interesting screencast. We are going to be solving this engineering mechanics problem, and it is determine the moment of inertia for the area about the x-axis as well as the y-axis. Problem is coming from the engineering mechanics of statics textbook, introduction by Hibbeler. So we want to find moment of inertia of the area, also called area moment of inertia, and also called second moment of area. This is a geometric property of a shape, such as a cross-section of a beam, that or which describes how the area is distributed around an axis where you want to find the moment of inertia. I mean moment of inertia of the area. Right. Mathematically, moment of inertia of an area about the x-axis I sub x is defined as equal to integral of y squared dA. Moment of inertia about the y-axis I sub y equal to integral of x squared dA. Right, it has several uses within disciplines of science and engineering. And if I was to give an example of just one discipline, which is structural and mechanical engineering, we use it for calculation of deflection of beams, for calculating load calculations of columns, and so many other applications within structural and mechanical engineering. Right, so let's quickly dive into this particular problem, which is a composite area. Okay, so it's a composite area. So first thing, we're going to define all the shapes first into regular shapes that we can work with. This particular composite shape or cross section can be defined in a number of different regular shapes. Okay, so what I'm going to define is not the only way. There are several ways in which you can define this. For me, I'll say let this be my triangle like this, and then I'll extend this line down, so that becomes my rectangle like so. So I have, and then I have this circle which is a hole. So I will still calculate this circle, and then I'll just give it a negative. I'll have to subtract it both in the x and in the y axis. When I find moment of inertia in the x, I'll subtract it in the x. When I find moment of inertia in the y, I'll subtract it in the y. Alright, so let's call this particular shape as my shape number 1, and the circle which is a 4, I'll call it shape number 2, and this other triangle there, I'll call it shape number 3, and this small rectangle here, I'll call it shape number 4. Alright, so now let's define the geometric properties. The equations that we're going to use to calculate this particular composite cross-section area is the parallel axis theorem. For moment of inertia in the x-axis, this is the mathematical expression I sub x is equal to Ix, that's moment of inertia about the centroidal axis, plus product of dy squared. This is a distance from the x-axis to the centroid of each of the shape times the area. The moment of inertia about the y-axis is equal to I sub y equal to Iyc. This is the moment of inertia about the centroid axis plus dx squared a. Alright, so these are the two equations that we're going to use for the two cases, since we'll calculate moment of inertia of an area both in the x and in the y axis. Good. So quickly, let's define the geometric properties. So which one do I start with? This one down. So let's say we have the centroid somewhere there. Okay, this one, and then let's say this one for this rectangle. I have a centroid somewhere there, and then triangle, let's say we have a centroid somewhere there. Okay, somewhere there, and then let's say the circle, of course we know the centroid is just there. Great. So quickly we have those centroids. Let's now do the measurements quickly. So draw a line like so there, like so. And then that is in the y direction. And then I'll go to this one. I'll go to this one like so. Let me just that I have some space. Okay, there we go. Alright, something like so. Then I'll go to okay, not this one. Let me get for the circle first. For the circle since it's inside. Okay, and then finally this one. And then finally that one. Yeah, I guess this is good maximization of space. Then let's go for the other one. Let me start with this one. This one like so. And then we'll go for the circle, choose this one. Go for the circle, choose this one. Okay. Alright. Then we go for this other one. Great. And then we go for this one. Okay. So like so. Great. So there we go. Let's now name them quickly. Let's name them. So let me just give them some few dots so that I don't mess up my space. Something like so. I'll just give it a little bit of dots so that I don't mess up my space. Sorry. Consuming your time. Great. Something like that. Great. So there we go. So that one, and then we have this as well as this. Okay. So what is this one? Let me use red. This one, I use red. This one is y held 4, right? Yes, y held 4. This is equal to half over 4. Y held 4 half over 4, and this is equal to 2 inches. And then we have this one. This one is for the circle, that's y held 2. That one is the circle. We have going up. That is up to what? Up to 4. That's 4, right? Yes. And then we have this one. This one. This one is y held 1, right? Y held 1 half of 6 plus 4, so half of 10, which is 5. And then finally we have this one. This one is y held. What is this one? This one is y held 3. this is equal to the height to that point is a 4 plus I tell 3, 4 plus 1/3 of 6. Okay, which gives us 3 into 6 is a 2, so 4 plus 2 is 6. So we have a 6. We are done with this. Let's go to this. So there we go. That one is x scaled 1, and this one is equal to half of 3. Half of 3 is just a 1.5. And then we have this one. We have this one. This one is x scaled. This is x scaled 2. That's a circle. This 4, which is equal to 1 plus 2, right? Okay. So this is 3 altogether, which is just a 3. Okay. And then finally we have this one. This one is x scaled x scaled 4. X scaled 4 is equal to 3 plus half of 3. So half of 3, which is equal to 4.5. And then we have this one, which is equal to that's for the triangle x scaled 3. This is equal to 3 plus 1/3 of 3, right? So this gives us a 4, right? Great. So we found everything. Let's find the area. So area 1 is equal to L times B, just LB. This is equal to 3 times 10, which is equal to 30. Then area 2 is equal to, this is a circle, pi r squared, which is just equal to pi 2 to the power 2, which is just a 4 pi. And then area 3 is equal to a half BH, which is equal to half B is a 3, H is a 6. So 2 into 6 is 3, 3 by 3 is 9. And then finally we have area 4. Area 4 is a what? Is a rectangle, is L times B, which is just equal to 3 by 4. This gives us a 4. Okay, let's find the centroidal moment sign, moments of inertia of an area. Great. So let's do that. Let me just give a small boundary there. Okay. What do we have? So we have moment of inertia about, to start with the x-axis, x1 equal to bh cubed divided by 4. So this one is of course a rectangle, so we know this is centroidal moment of inertia. B is just a 3, h is 10 to the power 3 divided by 4. So this is 10 cubed by 3 divided by 36. I mean 3 by 10 cubed divided by 4. So that gives us a 250. Okay. And then we have moment of inertia for step number 2, which is just a circle. So it's 1 over 2, 1 over 4, pi r to the power 4. So we have 1 over 4 pi, r is just a 2 squared. So this just gives us uh, 4.25 by 4. It just gives us a pi, right? Is that so? For sure. Gives us a pi. This is 2 squared, right? 2 squared, it just gives us a pi. Okay, great. It just gives us a pi. Okay, so let's move on. Oh no, to the power 4, sorry. This is to the power 4, not to the power 2. So this is the power 4. 4.25 by 2 to the power 4. That is 4 pi. Okay, then moment of inertia for shape number 3. That is about centroidal axis is 1 over 36 dh cubed. This is equal to 1 over 36. Our b is our 3, our h is our 6 to the power 3. What do we have? 3 times 6 cubed divided by 36. This gives us 18. The moment of inertia for shape number 4, which is just a rectangle dh cubed divided by 4. This is equal to b is 3, h is 4, to the power 3 divided by 4. So we have 3 by 4 cubed divided by 4. We have a 16. Alright, so we are done with the first phase. We continue with another phase about the y-axis. The moment of inertia about the y-axis for shape number 1. That's the dh cubed divided by 4. Okay, so our b in this case becomes a 10. Then our h becomes a 3 divided by 4. Okay, so we have 10 by 3 cubed divided by 4. This gives us a 22.5. The units here, they are inches to the power 4. The moment of inertia of shape number 2, which is a circle, is equal to moment of inertia about the x-axis. Okay, which is just equal to 4 pi. Alright, and then we have moment of inertia for shape number 3, which is a triangle. So it's 1 over 36 dh cubed is equal to 1 over 36. B in our case becomes a 6, h is a 3. When we do the calculation, 3 cubed by 6 divided by 36, we have a 4.5. And then we have moment of inertia for shape number 4. Okay, shape number 4 is a rectangle. This is just dh cubed divided by 4. It's going to be equal to our b in our case there will be 4. Our h is 3 to the power 3 divided by 4. When we do the calculation, we have 4 by 3 cubed divided by 4. This gives us a 9. So we are done with everything. All we just need to draw is now a table, 2 tables for that matter. We just need to draw 2 tables so that we fill in this information. So let's call this column part, then IYC, then X held, then area, then X held squared by area. Okay, let's draw this very quickly. We need 2 of them, so we don't need to make them so big, at least reasonable. Okay, so there we go. We have 4 shapes. So 1, 2, 3, 4, and confirmation. Right? Okay, great. So let's copy this. Copy this. Searching. We have 2 of them that we can make use of. Great. Right. Something like that. Okay. So let's fill in the information. Before we do so, let's just change here. We change there. We also change there. We change there too. Okay. There we go. So that one will be x centroid of x, and then there we are talking of y, then they are talking of y. Okay, so 1, 2, 3, 4 dimension, 1, 2, 3, 4 dimension. The area, let me enter the area first. We have a 30, we have a 4 pi, we have a 9. Okay, I think I extend this a little bit. I need some space there. I need some space, just a little bit of space. Some values will be longer. Alright, something like that. Alright. Okay. So we have 9 there. What else? We have a 4. Same here, 30, 4 pi, 9, 4. Centroid, the y, let's start with the y, no problem. And no matter which one you start with. Y1 is a 5. Y1 is a 5. Y2 is a 4. Y3 is a 6. And then Y4 is a 2. Great. And then X1, what is X1? X1 is 1.5. And then X2 is a 3. Then X3 is a 4. X3 where is it? Is a 4. And then X4 is a 4.5. Moment of inertia centroid about the y-axis. Y1 is a 22.5. Then the other one 22.5. Then for the circle, the second one is 4 pi. You have to indicate minus there, okay? You don't forget that minus because you're supposed to subtract. Then for the third one is third one is what? Moment of inertia. Third one is 4.5. The third shape, and then the fourth one is a 9. And then here about the x-axis, we have a 250, 250, and then we have a minus 4 pi, and then we have 18 and later 15. And when we take the products, 1.5 by 30, 1.5 squared by 30, we get a 67.5, and then a 3 squared by 4, we get a minus 36, a minus 36 pi, and then a 4 squared by 9, we get a 144, and then a 4.5 squared by 4, we get a 243. A 243. So when we sum up this, 243 plus 144 minus 36 pi plus 67.5, we have a 341.4027. When we sum up centroidal, 22.5 minus 4 pi plus 4.5 and plus 9, we have a 23.4336. The reason I'm putting 4 decimal places is just to maintain accuracy. The final answer will only have 2 decimal places. Alright, so let's find the final solution, final answer for moment about the moment about the y-axis. Moment about the y-axis is equal to moment about the centroidal y-axis plus dx squared area, then equal to 23.4336 plus 341.4027, and then when we add up that 23.4336 plus 341.4027, this gives us a 364.84 inches to the power 4. So this is moment of inertia about the y-axis. Okay, what do you think will be the value for moment of inertia about the x-axis? Which one do you think will be bigger between the y-axis and the x-axis? Of course, it looks like moment of inertia in the y-axis will be larger, right? Look at how the area is distributed, how big the area is. Alright, let's go ahead. So 5 squared times 30, that's a 750. Okay, that's a 750. Then 4 squared, 3 squared by 4, that's a minus 36 pi. And then 6 squared by 9, that's 324. And then finally, we have a 2 squared by 4, that gives us a 48. So 48 plus 324 minus 36 pi and plus 750, that gives us 750 minus sorry, this one here is not 36. That's 4 squared by 4. This is a 64. 64 pi. Okay, here we'll have another value. Okay, yes. 750 minus 64 pi plus 324 plus 48. So this gives us a 920.939381. Then the other side we have 250 minus 4 pi plus 18 plus 16. We have a 271.4336. Alright, so let's now find the total moment of inertia about the x-axis, which is equal to xt plus dy squared times area equals to 271.4336 plus 920.9381. This is finally equal to 271.4336 plus 920.9381. So what does this give us? Gives us a 1192.37 inches to the power 4. Okay, great. This is the final solution. This is the final solution for moment of inertia about the x-axis. And look at the value. About how many times? About 3 to 4 times. Or 3 to 4 times, 3 point something, It's really quite large. Right, I think this is about it. We are done with this particular problem, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing, and sharing my channel. I'll share the link for the other videos I've done for moment of inertia of an area. Bye bye, and see you in my next screen.